In this video, we're going to consider some diagnostic checks for the assumptions in ANOVA, as well as how to do the Boxcox transformations. So for this data, we are once again going to use what we read in before in the previous video, looking at the resin data. So I'm going to go ahead and read these in, and we can fit in our two models. Once again, as a reminder, be careful when you are running values where your response variable seems to be a continuous variable, but is in fact supposed to be categorical, to not run it this way, but to use this as.factor option to make sure that your degrees of freedom line up. Now, once we have fit an ANOVA model, R has a nice built-in easy method of checking the assumptions. We can use the plot function, and then notice I'm passing in AOV2, this saved object from the AOV function before. When we run this, we're able to come up here and hit return to see next plot. R is going to generate 4 plots for us. 2 of them are going to look similar, and we'll get to those in a moment, but our first plot is going to be this residual versus fitted. Now in this plot, this plot is setting us up to look at the assumption of constant variance. In order for these to be meeting that assumption, we should see approximately the same height for each of these bars. Now that being said, we're never going to see all of these be exactly equal, and so the tentative rule of thumb that we use is that we shouldn't see any one bar being, or length being, twice the length of another. This does look to be violated here. Our second assumption we can consider using this plot function is the assumption of normality, and we check this with a QQ plot. Now, if the data is normally distributed, we should expect to see the values lying very, very close to this reference line. Values shooting off below the line along the left or above the line on the right are indicative of this being not normally distributed, or other waviness or other values far off from this reference line would indicate that we have an assumption violated. The final 2 plots don't often get used as much. This first one looks very, very similar to our earlier one with our residuals and fitted values. In fact, it's doing the same. This is a plot that can be used to try to assess scale of the data, and again, it's not often used. The last plot, while often useful in certain circumstances, is not one that we consider in this class. It is looking for residuals that are leverage points. So if there are values in the data that tend to be pulling things towards a specific interpretation. Now, the last item we want to go over is the Boxcox transformation. Now, this transformation is, or this function to use this transformation, is within the mass package. So I'm going to go ahead and load that up. Now, the Boxcox function is going to perform this Boxcox transformation for us, and we need to, at a minimum, pass in a fitted ANOVA model. There are some additional arguments that we can pass in though, one of those being lambda, where lambda we pass in some set of numbers for values we want to check for possible transformation values. The default is -2 up to +2 with steps of 0.1, but you can choose other values. Now, if we run this way, we're going to get a plot that shows kind of this weird little curve. Now, what this curve is showing us is the likelihood of the data, or likelihood that a transformation is going to be beneficial. So what we should aim when we're doing this initial one is to have lambda values so that we get both a rising and falling portion for this curve. So I'm going to come back here and change this and allow this to go up to 4 for us so we can see enough of this curve coming down. What we tend to do is trying to come in and find a lambda value within these 2 error bars that we can use in order to perform our transformation, and then we can fit a new model with this. As a note, if your best lambda value lies within 0, then our transformation we use tends to be the natural log. And so what we can do, or another option we can do, is we can actually save the information from our Boxcox model. I'm just going to save some time here. But we can set an option of plot it equal to false, and this will fit the same Boxcox, but it's not going to give us this picture. Instead, it creates an object that contains all of the x values, meaning the possible lambda values, as well as the height of this curve, the log likelihood. And so we want to pick the value of x that is associated with the largest value of y, and that can be our proposed lambda. So I can use the which function and say, okay, I want the value in BC sub x, I want my largest, or the best x value, where, so which, where our BC sub y is equivalent to the max of BC sub y. And so if I fit this, I find a lambda value to use of 1.7. And so I can fit a new ANOVA model where now I'm going to take a transformation of y, and the Boxcox transformation is y raised to our lambda value minus 1, all divided by our lambda value. And then I'm going to have that be the same as it was before, as dot factor temp data equals resin. We can fit that, and now we have a new fitted object where we see our results here, still significant as they were before, and we can again use our plot function on AOV3, and we hope to see some values that meet our assumptions a little better. Though, in fact, in this case, we don't tend to see that. So this may be a data set where things are just a little bit hard. It's mostly this little group right here. If we ignored this group, everything would look nice. And then for our residuals, we definitely are a little closer to our line, but still perhaps not perfect. So, a final lesson that we can learn from this today. Unfortunately, sometimes things just don't work out as nicely as we would like them to.